It's my pleasure to welcome you to this fall's Minerva Lecture series that will be delivered by Barry Mazur. It is a personal pleasure for me that Barry will be giving these lectures. To start with, my first job was as a BP at Harvard, and I found that a bit scary, but Barry was always very friendly and welcoming. Second, Barry's brilliant work while a young Princeton graduate student, proving most of the topological Schoenflies conjecture in all dimensions, is an inspiration to all manifold topologists. In his 2013 lecture on the work of Barry Mazur and Marston Morse of the Institute, Mike Friedman described Barry's work as phantasmagorical. Now, I don't know what phantasmagorical means, so I looked it up in the dictionary. So one, having a fantastic or deceptive appearance as something in a dream or created by the imagination. Two, having the appearance of an optical illusion, especially one produced by magic lantern. It's a very apt description. So, in a moment, Professor Xiaoyu Tsang will give Professor Mazur a proper introduction. However, I'd first like to acknowledge the Fernholz Foundation for sponsoring these lectures. The Fernholz Foundation was created by Bob and Louisa Fernholz and is directed by Louisa Fernholz. We are very grateful to them for their generous support and long-time support of the department. And we're particularly pleased that they're able to attend this lecture. So it's my pleasure to welcome Professor Xiaoyu Tsang, who will introduce the speaker.
Well, it's my great honor to have this opportunity to introduce Barry Mazur. For number theorists, we know Barry by his work. I use two words. One is popularity, non-triviality. So it's very like everybody uses iPhone today. It's very easy to use, but if you open it, if you broke it, you cannot use it. You cannot really fix it. You have to return to the iPhone company. I mean, the first work for number theory, his work in the torsion points, you look at curve of Q. He gave a full list of this thing. But if you really want to understand the proof, the 150 pages manuscript, then you see how non-trivial this theorem, the proof of the theorem is, and how much new idea he gave for the following few generations of work to follow, including the proof of Fermat theorem and the work of Andreas and many others. And well, before I give a lecture, I really thought I know everything about Barry, the work. Just as I said, everybody knows iPhone. But so this morning, this afternoon, I started reading the Wikipedia. Then he has many work in the topology and other things. And he even invented some subject called arithmetic topology. Then I asked him, he said, no, I don't know what this field is. So, well, it's something about primes and the nuts. I guess I don't know what that thing is. Anyway, I'm glad Dave just gave a description of his work in topology, the Schoenflies conjecture. So I don't really have much thing to add. I think everybody knows Barry. And this event is just like an Apple event. What's the new thing you're going to announce?
That's scary. Thank you, Joe. I really appreciate it, Joe. And Dave, Dave reminded me that I was a graduate student here. And when I was a graduate student here, Google had not been invented. It being closer to 60 years than 50 years ago, I think. But the fine hole common room was, in some sense, the mathematical equivalent of Google. You could ask a question in any awkward or sort of incomprehensible way you wanted, and there would be someone in the, this is the old fine hole, but I'm sure the new fine hole is the same, and someone in the common room would say, oh, I know the answer to that, and would explain it, and usually explain it very well. It was a wonderful sort of little common room community that graduate students at that time essentially lived in. And I'm very happy to be here again and to be able to think about it. Okay, the picture you see on the screen is of David Hilbert, who sparked essentially a century of research programs in mathematics by his problems, and we're going to talk a little bit about the Hilbert's 10th problem, the problem about logic. As I was organizing these lectures, I kept thinking, yeah, I have a picture of Hilbert, but there's one other person whose, I think, viewpoint, at least over the 3 lectures, it may not be so clear the first, but in the second I will explain it a little more. The viewpoint is so so strong and so dominant. It's Serge Lang. I'm sure everybody in this room knows the name. His viewpoint towards arithmetic and Diophantine issues. Anyway, Hilbert's 10th problem is, as I've thrown it on the screen, I've tried to give as literal a English translation as possible. Given a Diophantine equation, to devise a process. I put the word process in red because if you think of it, the mathematics is filled with processes. I mean, beginning with, the Euclidean algorithm, for example, and you don't have to begin with that. You could take any of Euclid's so-called postulates, and they're all processes for constructing things. The thing about the use of that word in this paragraph, to devise a process according to which it can be determined in a finite number of operations, whether the equation is solvable in rational integers, what it did is it turned the word, thanks to the fact that you can't do it, as I hope everybody knows, it turned the word process from a simple word to a mathematical concept that people could begin to think about in a serious way. There are successes and non-successes in processes. For example, we have a lot of different processes in our experience. Linear programming, for one thing, or sort of procedures for factoring numbers. Basic questions we tend to ask are not, is there a process or is there not, if it's successful, because it is successful. What we tend to ask is, what kind of a process is it? For example, issues having to do with running time and so on. For the non-successes, well, we have quite a number. For example, there's no finite algorithm to determine, given a finite presentation of a group, whether or not the group is trivial. Or the recognition problem for manifolds in dimension 4 or higher is a non-success in this way of thinking. That is to say, it's unsolvable. And in the paragraph at the bottom of this screen, it being related directly to the recognition problem for finitely presented groups, that's, in some sense, the theme that keeps coming up. That is to say, if you have one sort of guaranteed non-success, there is no algorithm to do something, you try to piggyback on that to see what other non-successes you can sort of determine. And in fact, we'll be sort of thinking about that in at least the first two lectures. There's a funny thing about Hilbert's problem, because even when you look for interesting Diophantine examples, they don't sort of behave well very often. They often come in formats that's completely different from the way Hilbert's problem is posed. For example, we might be interested in polynomial equations over the rational field, or finitely or infinitely many solutions, that sort of thing. But most of the subtle distinctions, finitely many versus infinitely many, which requires an extra universal quantification in the logical scheme of things, is not a distinction that Hilbert at least explicitly formulated, but surely he sort of understood as one of the many possible parameters of variation of his 10th problem. And also, we're very often interested in families of problems. Not for a single polynomial equation, but rather for whole families of them. So, for example, the most, one of the most famous classical ones is the congruent number problem. The problem of determining those rational numbers that are the areas of right-angled triangles with three rational number sides. What we usually do is, instead of having rational numbers, and you can scale things by squares, of course, you usually list them in terms of the elementariness of the triangle that you started with, the heights, if you wish, of the edges of the triangle, but you only list the square-free part of it. That is to say, you form it to be a square-free integer, and you get this rather interesting collection of numbers, which has been the source of an immense number of even very recent work, as I learned this afternoon from Shawu. He has a student here, it's probably in the audience, Alex, who's working on a senior thesis in doing computations having to do with Selmer groups of elliptic curves. The reason why Selmer groups of elliptic curves might have anything to do with the series of red numbers I have on the screen is the question turns out to be equivalent to asking whether the equation, which I've put on the screen there, y squared equals x cubed minus r squared x, has or hasn't a rational solution with y different from 0. If it does, by the way, it has infinitely many rational solutions, but one would be enough to force that number to be a congruence. So back to Hilbert. Why, except for historical reasons, might you be interested in asking the sort of question that Hilbert asked? And one answer is that it just leads to interesting things. It's led to great developments in the intersection of mathematical logic and number theory. And also it calls for answers to new kinds of questions in number theory, and specifically the arithmetic of elliptic curves, which, at least in the third lecture, will expand to the arithmetic of varieties in general. So there's the program. The first lecture is just going to be about Hilbert's 10th problem and what I'll call Diophantine stability. We'll get to that in a moment. The second one will be elliptic curves and their rational points and why they are absolutely essential to logic. And the third will be actual methods. Okay. So once you begin to think of varying Hilbert's problem, you might ask, what about why work over the integers? Why not work over, say, things that are close to the integers, let us say finitely generated rings? Of course, infinite cardinality, otherwise it's no fun. So you could ask Hilbert's problem for some ring A. So given an infinite, finitely generated commutative ring A, And even commutative, as you'll see in the second lecture, is up for debate. Is there an algorithm to determine in finite time whether a polynomial in finitely many variables with coefficients in A has a solution or not? And just to make it absolutely clear what I mean in the input-output language, the input is a bunch of polynomials with coefficients in A, and your algorithm better give you a yes or no answering the question, is there a solution with entries in A? Now, so there is an industry for solving polynomial equations over finitely generated rings. And there's an immense amount of classical work. Some of the history I'm going to talk about in the second lecture too. But what I will consider the older work will have these four names as prominent. Julia Robinson, Martin Davis, Hilary Putnam, and Yuri Matiyasevich. And now there's a lot of sort of activity, very interesting activity by quite a number of people, which I've listed. And some of the things that I'll be saying will be related to their more recent work. Carl Rubin and I have a project studying the arithmetic of elliptic curves. And we were moved to sort of work on this Hilbert problem for finitely generated infinite commutative rings. And let me just say that we didn't answer the question. That is to say, we didn't answer the question unconditionally, but we proved a theorem. And it's a theorem that we want to think of as what we'll call a Diophantine stability result, having to do with the arithmetic of elliptic curves, that when you couple it with a standard conjecture in the field, gives what was needed to offer a negative answer for Hilbert's problem for any infinite but finitely generated commutative ring. And that's, of course, dependent on an immense amount of prior work, which I'll be talking about in a moment. But Diophantine stability, it's an elementary notion. I don't mean it to be a sort of a newfangled phrase. It's just shorthand in some sense for this. If you have L over K some field extension and a polynomial with coefficients in K, or maybe even a system of such polynomials, let's say that the polynomial is Diophantine stable for the extension L over K if it just acquires no new zeros over L. All the zeros that you would get over L were actually in K. Let us say all of the, if A1 up to A2 up to AN was a 0, where the AI are in L, then in fact those AI are in K. Then you say, natural phrase if you want, you say that the polynomial is Diophantine stable for the extension. Okay, now here's the thing. The reason why Diophantine stability and Hilbert's 10th problem is related is what we want to do is we want to transport undecidability from the ring of integers, say, of one field to the ring of integers of some larger field or ring. And the way we'll do it is we'll use the existence of elliptic curves that contain rational points of infinite order over the given number field. And that will be enough to sort of support anything that you would want to say about the logic over that, the ring of integers of that number field. And the minute it has Diophantine stability, it's saying exactly the same thing over the larger field. And so you've kind of bootstrapped undecidability from one field to another. And exactly how you do it may depend upon circumstance, and we'll try to discuss that a bit. Okay. Now, bootstrap, 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 but you have to start somewhere. And in fact, we could start earlier than this, but I'm going to start, at least in this discussion, with the classical work of Matiyasevich. In red, there's no algorithm for the ring A equals the integers. That is to say, thumbs down to Hilbert's 10th problem as Hilbert phrased it. Now, to say that there's no such algorithm, you might think is a negative statement. It's in fact a very strong positive statement. Because what he's going to do is use the known fact that there are subsets, I'll call them S, of the integers that are undecidable in the sense that although there might be an algorithm to list the elements of S, there's no algorithm to list the elements of the complement of S. So you can sort of, just like the congruent number problem with those red numbers on the screen a few minutes ago, you can list. And if you want to know whether 2 is in that list, you may never know, and especially if it isn't. Okay. That's one. And the second is, he's able to define any such listable set by a Diophantine method. And so it's clear that to the extent that listability has a kind of undecidability feature in it, he's conveyed that undecidability feature to Diophantine geometry, if you wish. So Diophantine formulations capture all listable sets. That's what he actually proves, including, of course, the undecidable ones. So you could take the positive view that Diophantine vocabulary is very rich. For example, I'm sure you don't want it, but this is a rhetorical question, if you wish. Once you see it, you won't want it. But do you want a polynomial over Z whose set of positive values is a set of exactly all prime numbers? When you make just arbitrary integer substitutions actually has 26 variables, so you can use the alphabet very nicely there. Well, here it is. I don't know what you're going to do with it, but if you have good eyesight, you'll see that it begins with k plus 2 times a curly bracket, and the whole thing ends with that curly bracket at the bottom. Now that's a bad omen for something that's supposed to be listing primes, right? Well, apparently not. The thing is, what's in that curly bracket, its maximum is 1. Okay? And it's 1 only when k plus 2 is a prime. Okay, so you win. Or I don't win, but there you are. Okay. In some sense, what Matiyasevich has done is he's shown that there's a sort of a real richness to the language of Diophantine analysis. Now, I use the word listable versus Diophantine. The way in which I've already refined Hilbert's question, even though it's on the screen now, is by resetting it as a problem related to listable sets and Diophantine sets. Now, it's interesting, half the complexity of the early history of the subject is in that word listable, I think. Because I didn't want to give a complete list of the synonyms of that as the subject matured. It was called recursively enumerable, computably enumerable. There are a number of other things. And that meant that there were a number of candidates for what it means to be able to list. And it wasn't clear at the beginning of the history of the subject that they were all the same. So you had sort of, quasi-listable, who knows? Finally, it settles down, and in fact, they are all the same. And so you can use the actual English word listable for it. Just as the word process in Hilbert's initial formulation of the problem is such a vague thing, but it rather rapidly turned into sort of a comprehensible notion of algorithm. Okay, a subset is listable. Here's the definition. There is a finite computer program whose output gives a sequence of integers, and L is that collection of integers. And a computer algorithm that does this job will be called something that lists L. Now, note that even if the computer spits out a new integer every second, the ordering in which the integers come from the computer's list may be very helter-skelter, even exactly as that congruent number list is, and that isn't as helter-skelter as they come. So running a helter-skelter computer program is not going to help you very much if you want to know about a number that actually isn't on the list. You'll never actually know. You prefer really listable sets. Sort of a more usable finite program would be a program that not only is going to list the set, but is going to give in sort of real time an actual estimate for how much time it's going to take to list all numbers of that set up to any number n. I'll call that a deluxe program. And now there's somewhere in between deluxe and listable. You can, somewhere in between would be a pair of computer programs that one of which spits out the elements of L and the other spits out the elements of the complement of L, and you do one by day and the other by night, and eventually you'll decide any question you might want to know about that list. And a set that has that dual type of computer program is called recursive. Okay? Now, the start of the subject, in some sense, is Alan Turing, and he proved that listable sets are not, that there are listable sets that aren't recursive. And he did this by the halting problem. He showed that there exists no universal algorithm to tell you whether or not any finite computer algorithm will terminate finitely when run. That's in some sense, the non-recursive type listable sets. And the halting set is just the set of couples where Px, where P is a program, and X is a possible input to the program, and such that the program will eventually halt if you run with the input X. This is the sort of primordial bad set that is piggybacked on quite substantially in proving undecidability issues. Okay, that being the case, let's talk about variants of Hilbert's problem. The most natural variant, and I keep wondering, and maybe some historian could give answers here, why didn't he ask it for Q? Why did he ask it for Z? It's kind of a little, he's being sort of very, I don't know why. Anyway, you can ask it for Q, and then you can ask people, well, do they think it's decidable or not decidable? And you'll get, opinions on both sides, I think. It's Peter. What?
I think mainly
against, yeah. The major guess is against, as you'll see in a moment why it's against. Yeah. Of course, you could ask for subfields of Q bar, or you can ask for small subfields of Q bar that are, say, finitely generated in finite degree over Q, or big ones. Well, Q bar itself, of course, is decidable. That's no problem. But once you get a little under Q bar, like real algebraic numbers and p-adic algebraic numbers, that is, these turn out to be really interesting questions, and I may get to them. And I hope I'll get to them. Yeah, maybe. Yeah, sure. Today. Here's something that even if the consensus for Hilbert's problem for the field Q is it's undecidable, I don't know what let's say a survey of number theorists would come up with if you ask for polynomials of degree 3 in many variables over Z. The reason why 3 is important is Matiyasevich produced a very beautiful, let's say, you can do it this way, is a one-parameter family of polynomials of degree 4 such that it's undecidable if you plug in values for the parameter whether there's an integral solution or not. On the other hand, for polynomials of degree 2, there's a decision procedure. So 3 is a cutoff, as it often is in Diophantine issues. Well, one can take a survey of guesses there. And then there's first order undecidability, so let me remind you about that. A Diophantine question just asks whether a quantity or a bunch of quantities exist. That's it, satisfying a Diophantine relation. A first order question might ask, for example, whether or not a quantity exists satisfying a specific relation to any quantity that satisfies some Diophantine relation. That would be a for all exists. For example, does there exist infinitely many something? You need a for all and then an exists. But and so on, you can keep going. You have for all W, does there exist an X? For all Y, does there exist a Z such that some Diophantine equation holds? So that's first order issues, first order sentences, and you might ask, do these type of questions admit an algorithm or not? And here the situation is much, let's say, more robust than the situation for Diophantine. The incompleteness theorem itself is enough to show that there's no algorithm to decide first order questions about Z. And then Julia Robinson piggybacks on that and bootstraps by a very beautiful construction. I'll show a variant of it in a moment. Using that, there's no algorithm to decide first order questions about the rational numbers or number fields or rings of integers in number fields. And it's done by bootstrapping to Z. And the blue little paragraph says, just says that the bootstrapping mechanism is if you can find a first order formula that defines the ring Z in a larger ring A, then Matiyasevich's theorem would show that there's no algorithm to decide first order questions about A. So we're looking for actually first order definitions of Z in various things. So here's there's something absolutely beautiful. I don't have enough time to list them all and to show how by small steps one gets to the sort of the favorite modern first order definitions of Z and Q. But here's Bjorn Poonen's first order definition of Z and Q. If you believe it, I mean, it's staggering as a thing. A rational number, T, is an integer. If for all pairs of rational numbers A, B, there are 7 rational numbers such that, what's classy is the 2309, the product. You can only imagine how one had to sweat to get that. Okay. And of course, the minute you have that, you have a bootstrap mechanism. You have a way of transporting things. So first ordered problems are undecidable over number fields and over their rings of integers, but what about undecidability versus decidability for big rings? And the landmark results are Hilbert's 10th problem itself is decidable over the ring of integers of all algebraic integers. If I said algebraic numbers, that would be trivial. Algebraic integers is the point. Van den Dries extends this to first order theory, decidable. There's work which shows that it's undecidable for the real algebraic integers, that is, the algebraic integers in, totally real algebraic integers, and for the ring of algebraic integers in the p-adics. Did I say totally real? I didn't mean that. Real. So there's lots of decidability for the big rings, so to speak. From the top, you have decidability, and from below, you have a little bit of undecidability for generally finite degree things. And so, can you squeeze them together? So, so as a result, Carl Rubin and I prove, and this definitely is basically Diophantine stability results. And here's the statement of the theorem, which has a kind of weird, it's a kind of weird statement you'll see in a moment. So let P be a prime number, or infinity. There are uncountably many subfields of K of the algebraic numbers in, say, the p-adics, in which there's a first-order definition of Z of the integers in K. And so it turns out that therefore the first-order theory for any such K and for its ring of algebraic numbers is undecidable. Now the weird thing is there aren't uncountably many definitions of anything, right? There are only a countable number of English sentences. So, so what's happening here, of course, is that any one of these definitions actually works for uncountably many fields. That is to say, you have a definition and you have the field. Now I don't know what language you have to define that field, but you have a bunch of fields determinable in some sense as a set, but you take any one of them and you apply that definition, you get a definition of, you get a definition of Z in K. So there's an issue that I think the logicians are beginning to sort of think as an interesting issue, that you have decidability up here and you have undecidability down here, and then one is beginning to squeeze. And the question is there any general conjecture you can make about the border territory where things switch? And I've heard some conjectures, but I don't think I have the authority to say what they are. I mean, they're not mine, but there seems to be some work in this direction. Okay, the minute you decide that Diophantine stability is an interesting thing, you can begin to ask for it in, say, a more general context. You can fix, say, a variety over a number field. Is there a non-trivial field extension for which that variety is Diophantine stable? That is to say, for which all k rational points of a variety subsume all L rational points. That any L rational point is a k rational point. Well, if V is the projective line, the answer is no. It has new points in absolutely every non-trivial extension. And of course, more generally, if you have one of these images of the projective line, or even an open subset of it in a variety, the answer is no for that variety for the same reason. So here's a question, curious question, once you begin to ask it. Is this the only obstruction to a positive answer to that question? Well, it's a question. And the question I've repeated here, V is a projective variety over a number field, such that for every non-trivial number field extension there are new points. Does V necessarily contain the image under a non-constant mapping defined over K of the projective line over K? And when V is a curve, the answer is yes. So that's sort of part of the Diophantine stability issues. Carl Rubin and I, and with help from Michael Larson, have proved that if V is a curve, the answer is yes. That is to say, not that the world has been waiting for another characterization of the projective line, but this is one. It's it's the only curve that has the property that it gets new points over every field extension. One way of organizing this is just to use the phrase belonging to, maybe. So if K is a number field and V is an irreducible algebraic variety over K, you might say that L over K belongs to V if L is generated over K by the coordinates of a single point of V. So, for example, this is a mild, simple theorem. It's not a tautology. Any elliptic curve over Q has infinitely many quadratic fields belonging to it. And you might consider the collection of all fields belonging to a variety and wonder sort of to what extent does that determine the variety. It's not going to determine it over the field, over the actual field over which it's defined, but it might be determined, for example, over Q bar. It's reminiscent of what people in studying, say, the arithmetic of elliptic curves. If you have an elliptic curve over a number field and you ask for the field generated by just its L-power torsion points, just the field, that's going to determine something pretty close to the elliptic curve. Not quite the elliptic curve, but it's isogeny class thanks to theorem of faulting. So anyway, it's an interesting collection of fields, which, and you can, of course, work both sides. You can fix a variety and study the extensions that belong to it, or you can fix an extension and study the varieties to which it belongs. So here there are two Diophantine stability results for elliptic curves. Before I it's not going to rotate. If you think of, there are two classical topics in the theory of elliptic curves, say over a number field. So this would be a number field, And you might have an elliptic curve over this number field. And you might ask for infinite extensions of that number field, which have the property that as you climb the infinite extension, you get Diophantine stability after a while. That's a standard question. And there's an immense amount of success and theory when this is, for example, the cyclotomic tower, that is, say, the tower of fields whose Galois group is ZP, obtained somehow by first adjoining all p-power roots of unity and restricting to a field that looks like that over the number field. We have a lot of results. I don't want to sort of go into them now, but we expect that it's stable after a while. On the other hand, there are other fields whose Galois group is still ZP, where we don't expect that. These are what are called, so these in the cyclotomic fields, we expect Diophantine stability after a while. In what are called the anti-cyclotomic fields, perhaps I'll put that here. And an anti-cyclotomic field is essentially a ZP extension such that there's an involution under the base which works in a dihedral way on that ZP extension. For these, it's a toss-up. I mean, sometimes you get more new points for the elliptic curve as far up as you get, as you want to go. These are usually produced by Heegner points, or sometimes you don't. But it is a toss-up. So those are very explicit and very specific types of fields. But suppose you take an arbitrary cyclic extension, not of infinite order, as these are, which would be of, these would be essentially unions of cyclic extensions of order L to the n for every n, but just take a board at an L to the n and ask what happens for these on a statistical basis. And here's a theorem that we prove. If E is an elliptic curve over K, and I'm just to organize it, there's no complex multiplication, that is to say, it has no endomorphisms other than multiplying by integers. And n is a positive integer. We prove that there are infinitely many primes L, where, for each of them, there are infinitely many cyclic extension fields of degree L to the n with Diophantine stability. Okay? And we prove, so that's going on the one side, that is, say, starting with the curve and considering the fields. But you can start with the fields and then consider the curves. And the theorem, the second theorem, which is in some sense part of the same package, it's actually harder, is you give me a cyclic extension, say of prime degree, it could be of prime power, but prime degree, then conditional on one of the standard conjectures in the theory of arithmetic of elliptic curves, that is to say the two-Shefarevich-Tate conjecture, there exists an elliptic curve which has the further property that its group of rational points is infinite cyclic and is Diophantine stable for that extension. And both these theorems have logical implications. The theorem, the second theorem has the implication of the statement that I gave at the beginning of the hour, namely that Hilbert's 10th problem is conditionally correct for all finitely generated infinite commutative rings. And the first one had that implication of uncountably many undecidable subfields of QP. But elliptic curves are elliptic curves. One can try to push for curves of positive genus. What does Beamer say? Okay. We show that for any curve of positive genus, there are really many extension fields that don't belong to it. That is to say, if X is an irreducible projective curve over a number field, not of genus 0, then maybe not over the initial field, but over some finite extension that you have to make once and for all. For any positive integer n, there are infinitely many primes L, where for each of them there are infinitely many cyclic extension fields L over K prime of degree L to the n with Diophantine stability. And we show this by relating curves to absolutely simple abelian varieties. We take, I'm going to, in the third lecture, I'll get into this. We take the curve, embedded in its Jacobian, project to an absolutely simple quotient, and we deal. We have a statistical question, therefore. You fix a curve of positive genus. Is it the case that our theorem, which only says that there are infinitely many L's and infinitely many degree L extensions, is it the case that for every prime number that's sufficiently large, almost every, that is 100%, of the cyclic degree L extensions of the base field K have the property that there's Diophantine stability. Now, you must, you probably recognize that every time anybody asks a statistical question, they have some sort of heuristic in their head. The heuristic may be good, may be bad, but they have a heuristic in their head. And if you trace the heuristic through its various layers of discussion, at the very end, the heuristic is always based on the fact that something is random. Of course, you could say, so the question is, what is random that would produce this? And perhaps I'll sort of hint at that in the remaining few minutes of the lecture. That conjecture, and also to some extent the theorem of Carl Rubin and myself, and is a kind of minimalist view that all in all, when you have a rational point of anything, you should rejoice. These rational points are rare. When they actually come in profusion, they better have some real graspable reason, maybe in an English sentence, and not just because they happen to happen. And so I'm going to discuss this in the next few lectures. Oh gosh, I'm doing a horrible thing. Yeah. Yeah, you can see it. And review it, the basics of elliptic curves and various tools, including Selmer groups of arbitrary number fields. In the end, we'll have to also know a little bit about representations of simple algebraic groups as well, but not that much. The statistics question I asked about that 100% has a sort of background in some actual conjectures and actual computations coming from essentially spurred by random matrix statistics. In the remaining few minutes, I'm going to sort of be a little more technical, maybe not too much more technical, but anyway. And this is the work of David, Fernley, and Kiselewski. They conjecture. They're now over Q because they're actually going to compute. They're going to produce data. And they conjecture that for a fixed elliptic curve over Q, and for any prime L that's greater than or equal to 7, there are only finitely many non-Diophantine stable cyclic extensions of Q of degree L. That's a much fiercer conjecture than the one I put on the screen a few minutes ago. That's one thing. And also they begin to look. And when they look, they've only been able to find one with L equals 11. And they've looked. So why did they conjecture this in the first place? In fact, for L equals 3 and 5, they really made use of their random matrix heuristics and began to produce very estimate conjectures about the number of cyclic extensions of degree L that are cut out by a Dirichlet character of order L and a conductor less than or equal to some x, and they conjecture certain rates of growth here of them. Now, they use random matrix statistics, and in the next 5 minutes, I'm going to sort of, anyway, show you something and ask your indulgence. They use random matrix statistics. Now, in this game of trying to compute how often you get extra points let us say, necessarily if L is large enough of infinite order on an elliptic curve, you're dealing with L functions, and the information is contained in certain essentially integer valued functions, which are called modular symbols, attached to rational numbers a over n, so that if you have a trigonometric sum of these modular symbols weighted by a character chi, and if that trigonometric sum is plunk 0, then the L function of the elliptic curve at chi at the central point is 0, and then by conjecture you would expect that the field extension, the cyclic field extension of degree L cut out by that character chi would have extra points. So you want to know how often is it 0. And if the modular symbol therefore has all that information, and if the modular symbol were random, you would essentially repeat the random matrix heuristics. And so Carl Rubin and William Stein and I decided, hey, let's compute a little, see whether it's random. Now, the way in which we decided to compute was we took the function capital G is the sum of these modular symbols for rational numbers between 0 and tau as a function of tau. Now, that is supposed to be a stupid number. And if the modular symbol were totally random, it would... but of course, it's not a stupid number. In fact, we conjecture that it's equal to the convergent function given by the expression here, where the ANs are the coefficients of the L function of the elliptic curve. And we conjecture that the limit is fairly fast. And here's our computations. Here is on the left is the stupid sum of the modular symbols up to tau. On the right is the function. Now, we wanted to blow this up to show you that we're not kidding. That is, say, every little quirk in the one has a quirk in the other. And so if we do that, we have to show you full screen. So there's for 37. This is the one on the left. This is the sum of the modular symbols up to tau is the graph of it. So to speak, the integral of the step function determined by the modular symbol. And exactly the same thing is for this. Now, it's not a mystery that we would conjecture that. One can think of it. But what seems to be mystery to us is how fast the convergence is. And we're open to suggestions as to how to prove it, and especially how to prove it with error terms. So the modular symbols are not random, but they seem to be so convergent to this non-random thing that that's okay. The error term still may be random. So that's what we're looking at. Anyway, so this is our sort of a mini project of computation. There's lots of computation to be done if any of the graduate students are interested. That'd be good. Okay. We're going to see that tomorrow.
Maybe elliptic curves is like the next step.
You're stealing my show. The thing about the Pell equation is that it is not Diophantine stable. Okay.
Yeah.
All right. But still come to my lecture.
More question?
Yeah.
Charlie?
Hi.
Suppose that you have two extensions of the rationals, a bigger one and a smaller one contained in it.
Yeah.
What what is obvious and what is known about the relationship between, let's say, Diophantine things happening, one versus the other?
Basically independent. I mean, you know, you might imagine, you're thinking of the big one first. What if we start with the little one first,
Right.
and then look for some bigger one?
Mm-hmm.
I think it's, what I like about this is that there is a real dependence in that, did you mean it to be cyclic maybe?
Okay.
Because this is infinite cyclic, and on this, and both of them, you would say, well, why should a field extension this far out know that much or care that much about a field extension that's closer to the base?
Yeah.
The answer is it must care because eventually there's going to be Diophantine stability, but it's an asymptotic thing. But if you just give me 2, that's not enough. I mean, if you gave me a lot, if you give me L to the n for large n, then yes, then we can begin to see some sort of that the higher extensions know more and more and more about the lower extensions. In this situation, it's absolutely clear that these extensions know something about a sub-extension of the base here, because if there is an involution that operated in a dihedral way on this, you would have a completely different expectation for what's going to happen. But still, it's asymptotic.
So it seems like it's not so hard to make a lot of vectors on the curve, but you're saying
That's correct. That's correct. In fact, one of the things that would be really interesting to do is to on this. You see, I wouldn't do it with points because it's too hard. But with the Selmer rank, you can prove theorems that if you have a sort of seriously dihedral situation, the Selmer rank is going to grow. So yeah.
So can you say like which group suits that? Like most G extensions?
You want me to generalize it to an arbitrary group? Oh, I would say solvable group. No, that's cheating. That's cheating. Okay, I've actually begun to think about it. The dihedral ones are really bad, and there should be asymptotics about this. But still, if you have a simple group like the alternating groups, there are some interesting things you can look at, and nobody's looked at this actually, but it's worth doing.
Are you the only guy who thinks that things are good over Q?
No, I don't think they're good.
Are you done?
No,
So who does?
I used to.
All right.
What do you think about degree 3?
No, you're right. That's probably good.
What?
I think it's good.
You think it's good? Well, the thing about degree 3 is if you're a number theorist, you have to think it's good. Because then you work to find the algorithm. I mean, it's a bad strategy to think it's bad.